All right, welcome to Homework Help for Unit 8, Lesson 3, Slippery Slopes. So we're going to start with the ready, which starts with number 2. That's the first one that is assigned for today. So we're going to solve for h. And for all of these, we are just going to take some formula or some equation and solve for a given variable. So in this case, we're solving for h. So let's get right to it. So v equals pi r squared h. Okay. This is the volume formula for a cylinder. So what we're going to start with is getting h alone. So I notice here that we have v equals pi r squared h, and pi, r squared, and h are all multiplied together, which means we can just divide everything that's not h from that right side. So what we're going to do to start is divide both sides by pi r squared. Right? Divide both sides by pi r squared. And what we're left with is, right, v divided by pi r squared is equal to pi r squared h, right, pi r squared h divided by pi r squared, right? And you can see that these parts cancel, right, because they're the same. So v over pi r squared equals h. All right, our first question is complete. Solve for b. Okay, this one's going to be a little bit trickier. We'll switch it to be, let's go purple. Let's do that. All right, a squared plus b squared equals c squared. Do we know this one? Does this ring a bell? Maybe, maybe not. This is Pythagorean theorem. A squared plus b squared equals c squared, where each of these is a side of a triangle, specifically a right triangle. So we're solving for b. All right, we need to get b by itself. So the first thing we're going to do is subtract a squared from both sides. Subtract a squared, subtract a squared. What are we left with? B squared equals c squared minus a squared. All right. Okay. Then we want to solve for b. Right? We just want to solve for b without any of the squared bit. So we are going to take the square root of both sides. And normally in a question like this, we would just take the positive square root. But because we're doing this like purely mathematically and it's not actually geometry how we're doing it right now, we're going to take the positive or negative square root of both sides. Positive or negative square root of both sides. Positive or negative square root of both sides. So this becomes b equals the positive or negative square root of c squared minus a squared. There we go. That is number 4 completed. All right, let's keep going on and keep chugging away. All right, solve for x. All right, we're solving for x here. There's an x here and there's an x there. So this is going to be a little bit tricky. How are we going to do this? Well, the first thing we definitely have to do is make sure that our x's are all on the same side. So let's move this x over here. Wait, sorry, let's move this x so it's going to be over there. So let's add 2x to both sides. Okay. And when we do that, we will have 65 equals, there we go, 20 plus wx plus 2x. Okay. And then we have this number, this 20 is on the wrong side. So let's subtract 20 from both sides. Minus 20 minus 20. And we're going to have 45 equals wx plus 2x. We're going to move this up here so we have a little bit more room. All right, and rewrite it just exactly as it was. 45 equals wx plus 2x plus 2x. Now what are we dealing with? We have x's in both of these, which means we need the x's to be left together. So actually, what if we pull the x out? What if we did that? Let's factor this right side. Right? These have a common factor of x, so let's rewrite this. 45 equals, and we're going to pull the x out, x times w plus 2. Right? Because if we were to, right, this is factored form now. If we were to expand this, we'd say x times w is, wx, and x times 2 is 2x. So this is where we are now, right? This is just factoring. And finally, we're going to divide both sides by w plus 2. Divide both sides by w plus 2. And we'll even put it in parentheses to make sure that it is very clear what we're doing. We're dividing both sides by w plus 2. So we get 45 divided by w plus 2 equals, and what's left over here? If we divide x divided by w plus 2, or sorry, x times w plus 2 divided by w plus 2, we get just the x. And what were we trying to do here? We were trying to solve for x. So there we go. We have solved for x. And that's the bottom of the page. All right, up to the top. All right, we're still going. Solve for C. We'll go with the purple. Solve for C. E equals mc squared. Anybody know this one? No, this one's from Albert Einstein, I believe. But E being energy equals mass times the speed of light squared. Is that right? E equals mc squared. I believe that's correct. Speed of light squared is it's very, very fast. Anywho, let's carry on here. Formula, E equals mc squared. We want to solve for C. All right, so the first thing we're going to do is divide both sides by m. Divide by m, divide by m. We now get E divided by m equals c squared. All right, now we're going to copy this up so we have a little bit more space. E divided by m equals c squared. We're going to take the positive or negative square root of both sides. Positive or negative square root of both sides. And we get the positive or negative square root of E. Oop, that didn't quite work. Of E divided by m equals C. So we've solved for C there, and now finally solve for m. K equals 1/2 mv squared. So this is kinetic energy equals 1/2 of the mass times the velocity squared. I do know that one. So let's do this. K equals 1/2 mv squared. Solve for m. All right, let's get rid of the 1/2 first. We'll multiply by 2 times 2 on both sides. Times 2 times 2. All right, we get 2k equals mv squared. And we're going to take this up here. 2k equals mv squared. mv squared. Then we're going to divide both sides by v squared. Divide by v squared. And we get 2k over v squared equals just the m is left. All right, so we're done with that one. On to the set. Complete the mathematical statements about the kite using the given symbols. Show that the statement is true. All right. Let's look at our symbols. All right, we can use the congruency symbol, the perpendicular symbol, the parallel symbol, less than, greater than, and equal to. All right, those are the options. All right, so that's a lot. That's a lot to consider. So let's see, BC and DC. All right, BC and DC. I'm going to highlight them in a color, but then I'm actually going to go and erase it once we're done with the question, because we're going to keep having, we have to keep using this same graph, so, or the same picture. So we're going to highlight it just to show what we're talking about, and then we're going to go and erase it. So BC is something, right? There's some symbol, and DC. So BC is here, and DC is here. So those are the two things we're looking at, BC and DC. Okay. So we're talking about a kite, right? So a kite, we know that in a kite, like these two will be congruent and these two will be congruent. And then we also know, right, it's a property of a kite that those are going to be right angles, right? There are going to be some right angles where the diagonals intersect. But let's assume we don't know that. Let's figure out, right, we're comparing two different, okay, actually, BC and DC, right? You'll notice there's not a, do you see how there's not a line segment here, right? That tells me, right, if we're not talking about a line segment, right, BC without the line on top is saying compare those distances instead of comparing the actual segments. So, so that's important, because if we're looking at BC and DC without those symbols, right, we're immediately looking here, right? This is going to be distance, and this is going to be for like segments and triangles. Nope, not a comment. Seg. And we'll finish writing out distance, that's fine. Okay, so this is a distance. So we're looking at, let's erase the stuff we've put on here. That's fine. So we're looking at the distance. So what is the distance from B to C? Well, we have the point 0.03. I will write in that this point, right, we're looking at this compared to this. And this is the point 4, 0. So the distance from B to C, it looks like it is a, it's a 3, 4, 5 triangle. So 3, we know that it's a right. What's the most efficient way of doing this? We'll just do a distance formula. That's fine. So we have 3 squared, right, from 3 to 0, right? We have 3 minus 0 squared, that's the y's, plus 0 minus 4 squared. So that's going to be equal to the square root of 3 squared plus negative 4 squared. Negative 4 squared, which the square root of 9 plus 16 is the square root of 25, which is 5. So that's 5, right? BC is 5. And DC, well, we're just going from 4, 5 to 4, 0, right? That's also going to be 5. So, so the symbol we're looking for is going to be equal. Equal symbol to start. All right. BD and AC. All right, so let's, we said we were going to erase once we're on to the next one. There we go. And we'll switch colors as well. BD and AC, and now we're looking at segments. Now we're looking at segments, right? Because there's the little line on top. It's segment BD and segment AC. So BD oh, hang on. BD is here, and AC is here. All right, so we're looking at these two. So segment BD and segment AC. Well, segment BD, we could compare the, if we're looking at segments, are they congruent? It looks to me like one is longer than the other. So I think it would be wise to look at perpendicular versus parallel. Now, they don't look like they're parallel, so I'm going to check perpendicular first. I'm going to check perpendicular first. So let's see if BD and AC, oh, I'm sorry, the proof on the previous one was up here, right? Because we calculated that it was equal to 5. So BD and AC, and we're looking for proving perpendicular, right? So perpendicular means opposite reciprocal slopes, right? So if we can find opposite reciprocal slopes between these two, then we know it's perpendicular. So the slope of BD, it looks like it goes from 0, 3 to 4, 5. So the change in y is 5 minus 3. And the change in x is 4 minus 0. Oh, I didn't like that. 4 minus 0. So the slope is 2. 5 minus 3 is 2. Over 4 minus 0 is 4. So the slope is 1/2. And then the slope of, I'm going to go down just a little bit so I can write a little more comfortably. The slope of AC, that's the other one we're looking at. The slope of AC is going to be, we'll use A as our top one, or as our first point. So that's going to be the y first, so 6 minus the y value for point C, which is 0, 6 minus 0, divided by, and then we'll go back to A, 1 minus 4. 1 minus 4. Okay, so slope AC equals 6 minus 0 over 1 minus 4, right? Or six minus 0 is 6. 1 minus 4 is -3. 6 divided by -3 is just 2 divided by -1. So we have -2. So they are opposite reciprocals. Opposite reciprocal, which means perpendicular. So we go over here and we write our little perpendicular logo. It's a perpendicular symbol with or without the little box. So up here, right up where they give the symbols, there's no box. You can put the little sort of square to show it's a right angle. I like to do that, so it's very clear that I'm not writing like a plus sign. But you don't have to. You don't have to if you don't want to. Let's go back and okay. 14, we're looking at triangle ABC and triangle ADC. ABC and ADC. So let's first erase. We're interested in triangle ABC and ADC. Go back to green. All right, ABC is here. ABC is here. And ADC is here. So we're looking at these two triangles. They look to me like they're going to be congruent, right? If we're looking at two triangles, we either can say that they're congruent or we can say that they're not congruent. Those are the only symbols we have available. None of the other symbols make sense. Triangles can't be perpendicular to each other. They can't be parallel to each other, they can't be greater than or less than each other, and they can't be equal to each other, because if they're equal, we just say they're congruent. So the only option for these symbols to go in there would be congruent. So we're going to put congruent in that box, right? We're going to put congruent in the box, and now we have to prove it. So what would we need in order for ABC to be congruent to ADC? Well, we would need a couple of things, but what do we already know? We know BC and DC are the same length, right? So we know that BC and DC are the same length. We know that A to C is the same as A to C, right? It's the same length as itself. So to make sure the triangles are the same, the only thing we're missing is B to A being the same as D to A. So let's figure that out. B to A and D to A. Right, and have we done that yet? No, we have not. So let's find out B to A and D to A. All right. So we're proving that BA has to be equal to DA. That's what we have to prove. And if we can prove that, we will be in good shape, because then we have SSS triangle congruency. So BA and DA. So from B to A is 0,3 to 1,6. Right? B to A is 0,3 to 1,6. All right. What is the distance there? That's going to be the square root of 6 minus, we'll go 6 minus 3 squared plus 1 minus 0 squared. That's going to be the square root of 3 squared plus 1. And that's the square root of 10. Okay. Now we go up here and we say D to A. Right? What are the points D and A, right? So D is 4, 5, and A is 1, 6. So 4, 5 to 1, 6. 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 And we set up our square root, right? Same thing, but now instead of writing 0, 3, right? Instead of using the 0, 3 point, we're going to write the other point. So this is going to be 6 minus 5 squared plus 1 minus 4 squared. 6 minus 5 squared, well, 6 minus 5 is just 1. So that's 1 squared plus 1 minus 4 is negative 3 squared. Then we do this, we get 1 squared is 1 plus negative 3 squared is 9. Didn't like that, plus 9. So that's the square root of 10. All right, so we've proven that, right? So our proof is that those are both equal to the square root of 10. So then we have the triangles are congruent by side, side, side triangle congruency, right? So because we've just stated that, right, we've just proven in question 11, we proved that BC and DC were the same, right? So BC, or this bottom left, and DC, our bottom right, those segments are the same length, so we can put congruency markings. And then the middle line, right, the line that's shared between the two triangles has to be the same length in both triangles, because it's the same segment and it's used in both triangles. So that's A to C is the same length as itself. So that matches in both triangles. And then we just use distance formula to prove that BA and DA are the same length. So we can finally add this last, right, 1, 2, 3, 1, 2, 3. So those are the same distance as well. And we can move on to the next one, which means we are going to erase all of our congruency and markings so we can use a clean slate on the next one. And what do we have left? We just have 17. AC and BD. All right, AC and BD. AC, that's one of our crossovers, right? AC here and BD here. And now the question is, right, didn't we already do AC and BD? We did, right? Question 12 was BD and AC, but it was asking about the segments, right? And the segments means that we're looking at, right, congruency, perpendicular, parallel. If we look back at question 17, AC and BD, but these are not segments, these are just distances. It's however far it is from A to C compared to however far it is from B to D. So when we go back, we're just looking at distances now, right? So we're looking at we are looking at whether, right, A to C is less than B to D, greater than B to D, or if the two are equal. So let's go figure out what our distances are, and we're going to need to copy our points down. So let's do that. So I'm going to do this in purple, I believe. So A to C uses 1, 6, and 4, 0. Right? 1, 6, and 4, 0. All right. B to D uses 0, 3, and 4, 5. 0, 3, nope. 0, 3, and 4, 5. All right. Now let's get cracking here. We got some distance formulas to do. Here we go. All right. Setting up the first one. What is the distance from A to C? Well, it's going to be, I'm going to zoom in a little bit more here. I want to use the space effectively. Here we go. 1, 6 to 4, 0. We'll do the x's first. Doesn't really matter. But we'll do the left minus the right. Let's do that. 1 minus 4 squared plus 6 minus 0 squared. Right, this will work. When we simplify this down, we get 1 minus 4 is negative 3 squared plus, this is just going to be 6 squared. And this becomes negative 3 squared is 9, so this is the square root of 9 plus 36. So this is the square root of 45. Okay. So that's one of our lengths. So the length AC is the square root of 45. Now let's look at BD. Right? Start with 0 minus 4 squared plus 3 minus 5 squared. Okay. 0 minus 4 is negative 4 squared plus 3 minus 5 is negative 2 squared. Negative 4 squared is 16 plus negative 2 squared is 4. So this is going to be the square root of 20. All right. So which one's greater? Is the square root of 45 bigger, or is the square root of 20 bigger? The square root of 45 is going to be bigger. Pretty significant difference here. So AC was the one that had the square root of 45. So AC is greater than BD. And our proof is that the square root of 45 is greater than the square root of 20. Right? because those were the distances, right, or the lengths of each one, right? AC is greater than BD. And if we look back at it, it sure looks like A to D, or sorry, A to C rather, it looks much longer than B to D. Maybe not quite twice as far, but it is definitely longer. So let's move on to the go. Use the given information to write the equation of the line in standard form. Our slope is -1/4, and a point that we have is 12, 5. All right. Well, let's see. What do we have to work with here? We have a slope and a point. Now, it would be really easy to write this equation in point-slope form, don't you think? Right, because we have slope and a point. So we can start with that. I mean, we can always start by writing it in point-slope form. Let's do that. Let's use green. So if we wrote in point-slope form, that would be y minus our y value, which is 5, y minus 5, equals our slope, -1/4, -1/4, x minus the x value we are given, which is 12. Now all we want to do, in order to put this into standard form, is get our x's and y's on one side, and just a number on the other side. So let's do that. Let's go first expand. Y minus 5 equals -1/4 x plus, what's a quarter times 12? I think that's 3, plus 3. Okay, all we did was expand in that step. Now we're going to add 5 to both sides. Let's do that. Add 5 to both sides. Okay. Y equals, oh, come on. Y, we'll go back. Y equals -1/4 or 1/4 x or 1/4 x plus 8. Let's add 1/4 x to both sides. Go up here. Let's go y equals -1/4 x plus 8. We're going to add 1/4 x to both sides, add 1/4 x to both sides, add 1/4 x to both sides. So we get y plus 1/4 x equals 8. And then let's multiply. We don't really like having fractions. So, I mean, this is fine, right? This is standard form. But typically for standard form, we want to have only integers, not fractions. So we're going to keep going and actually multiply both sides by 4 times 4 times 4. So we get 4y plus x equals 32. That is going to be like a much nicer thing to deal with, much nicer standard form equation to deal with. So that wraps up. Oh, does it? Hang on, that's 18. I believe that wraps it up because none of these are circled, and I did a pretty thorough job circling at the beginning, so I believe that wraps up. What is this? Unit 8, lesson 2 or lesson 3? Which one is this? Unit 8, lesson 3. That wraps up Unit 8, lesson 3. Hope it was helpful.